Ever wondered how AI got so powerful, so fast? Well, a huge piece of that puzzle is a single, brilliant idea that allowed computer brains' neural networks to become unbelievably deep. Today, we're diving into ResNet, the architecture that cracked a baffling problem and basically changed AI forever. Let's get into it.
So, to really get why ResNet was such a big deal, we have to rewind to the early 2010s. The computer vision world was in the middle of this absolute frenzy. The mantra back then was simple: deeper is better. The more layers you could cram into a neural network, the smarter it was supposed to get. And this slide right here, it just perfectly captures that race. You're looking at the winners of the big annual image recognition competition, and the pattern is impossible to miss. In 2012, you had AlexNet with 8 layers. A couple of years later, VGG comes along with 19. Then GoogleNet pushes it to 22. Every single year, the winner was deeper and the performance was better. It was this relentless march towards more and more depth. So this led everyone to the million-dollar question, right? If deeper is always better, why not just keep stacking layers? Let's go from 22 layers to 50 to 100 to 1,000. Can we just build this unbeatable super deep model? Well, the answer, as researchers were about to find out, was a very, very surprising no. Instead of this amazing breakthrough, researchers just hit a wall. They ran smack into this really weird and totally counterintuitive problem they ended up calling the degradation problem. Okay, so check out this chart from the original ResNet paper. It tells the whole story. The orangish line, that's the error for a shallow 20-layer network. The blue line is for a much deeper 56-layer network. Now, common sense says the deeper network should be way more accurate, right? Lower error. But look at it. The blue line is always higher. The deeper network was actually worse. And not just on new data, it was worse on the very data it was trained on. It made no sense. Now, usually, the first suspect for any machine learning pro is something called overfitting. That's where a model just memorizes the training data too well. But that wasn't it. The fact that the training error itself was getting worse meant something much more fundamental was broken here. The mystery deepened. So, the authors of the ResNet paper had this hypothesis. It's not that a deeper network couldn't be better. The problem was that it was just brutally difficult to train. The optimization process, the way these networks learn, was getting completely lost, unable to find its way to a good solution. So stuck at this frustrating roadblock, a team at Microsoft Research Asia had this incredible aha moment. They came up with a solution that was so simple, yet so profound. They called it a residual network, or as we all know it, ResNet. All right, on the left, you've got the old way of doing things. Information goes through layer 1, gets processed, goes to layer 2, and so on. It's a straight line, but as we saw, this breaks down when it gets too deep. Now look at the right. That's the ResNet solution. See that curved arrow jumping over the blocks? That's the magic trick. It's a shortcut connection. It lets the original information just bypass the processing layers entirely and get added back in later. It's basically an information express lane. And here's the genius part. With this shortcut, the network doesn't have to learn a whole complicated transformation from scratch anymore. Instead, the shortcut carries the original input forward, and the layers only have to learn the small change, the residual, that's needed to improve the result. Think about it. It's way easier to learn how to make a small correction than it is to learn an entire complex task from a blank slate. And that right there is the core idea. These shortcuts let the network just pass the input through unchanged if it needs to. This is called identity mapping. The layers can then focus all their power on the much easier job of figuring out the residual, or the difference. It's this one simple trick that suddenly made training ridiculously deep networks not just possible but effective. So the big question is, did it actually work? Oh yeah, it didn't just work, it completely changed the game. This simple idea didn't just fix the degradation problem, it created an architecture that would go on to dominate the entire field.
You know what's wild is that building one of these massive ResNets is actually pretty straightforward. You start with a standard image processing layer, and then you just stack these little residual blocks we just talked about, one after another. Dozens of them. You make some tweaks here and there, and then finish it off with a simple classification layer. It's like building with superpowered Legos. And the result of all this? This number. At the 2015 ImageNet competition, the 152-layer ResNet model achieved a top 5 error rate of just 3.57%. I mean, that number was just unbelievable at the time. It wasn't just a tiny step forward, it was a giant leap.
And look, this wasn't just about winning one little category. ResNet absolutely cleaned house. It took first place in all 5 main events at the major computer vision competitions that year. And we're not talking about squeaking by with a narrow win. In some cases, the second-place finisher wasn't even close. It was pure dominance.
And here's the real mind-blowing part. That 3.57% error rate, it was so low that it was officially better than the estimated performance of a human expert trying to do the same task. That's right. For the first time on this benchmark, a computer model had actually surpassed human-level accuracy. That was a huge moment for AI. So after 2015, the world of deep learning was just different. ResNet didn't just win a trophy. It gave everyone a completely new blueprint for how to build incredibly powerful AI. This chart does a great job of showing you exactly what that means. You've got accuracy going up on the vertical axis and how much computer power it takes on the horizontal. See the old VGG networks? They're expensive for the accuracy you get. GoogleNet was super efficient. But then look at the ResNet models in pink and red. They just blew past everyone else, pushing the absolute limit of accuracy while staying pretty efficient. They created a whole new frontier. So when you boil it all down, ResNet's legacy is just huge. It suddenly made it possible to train networks with hundreds, even thousands of layers. That simple little shortcut connection is now a standard fundamental piece of so many modern AI systems, from the models that generate images to the large language models powering chatbots. It kicked off a whole new wave of architectures and totally changed how researchers thought about building AI. You know, when you think about it, ResNet's magic wasn't just about brute force or adding more layers. It was about thinking smarter. It was about reframing a hard problem to make it dramatically easier to solve. It showed us that sometimes the best way to get over a giant wall is to build a simple shortcut. And it makes you wonder, right? What other huge, complex problems out there, maybe in science or even in our own lives, are just waiting for someone to find that one elegant shortcut that changes everything?